Hey guys, this is my ABE424 2020 final project where I made a virtual oscilloscope using MATLAB. Hope you guys are doing well and I'll get right into it. So first off, I used 3 callbacks: startup FCN, acquire data button value changed, and cat's knob value changed. Similarly to their name, startup function is used for when the app just starts up. Acquire data button value changed is when a button is pressed, and cat's knob value changed is a fun personalized thing I just added in. You'll see it in the works when I show you my app. I will be explaining mainly the acquire data button value changed callback function because it is the button that makes all the magic happen on the app, and I'll briefly cover the other two as well. So first, my startup FCN app simply starts the DAC session and doesn't do anything at first. The reason that my startup FCN has nothing is because I don't want the app to do anything before I click or operate with it. The cat's knob value changed function is for changing an image in my app. This function receives a value from the knob, and through the various if statements, it compares the grabbed value to a string. If the string matches up, then the image is replaced by a JPEG that I have in the folder. As I said earlier, you'll get to see this in action when I show the app. This final callback function can be considered the catalyst for my app. When the user inputs everything they need to input, such as the NR data and the mode, and when they click on the button, this function activates. To just walk you through this function, when the button is pressed, the value becomes 1, and we set our global variables to the numbers set by the user, and the DAC active lamp will turn green. Meanwhile, the status bar will show acquiring data, and the button will change its label to working, so you don't accidentally double click. If you double click on the button, it will probably crash. The global variable, in all caps, data, will be set to the return value of a helper function, getData. The display signal function will display all the variables and the plots needed for the time domain part of this project, while display FFT will display the frequency, period, acquisition time, and sampling per second, and finally the plot. Once all of these helper functions finish plotting and doing its thing, the status will change to data acquisition successful, and at the end of the if statement, the button value goes back to 0. The lamp color goes back to red, and the button text returns to acquire data. Moving on, the helper functions that you saw in the previous slide is where all the math and plotting comes from. I'll go through getData, display signal, and display FFT in detail. So the getData function is similar to its name. It gets the data based on what the user inputs for the NR data and the mode. The if statements compare the mode value selected and the string corresponding to it and obtains the data related to it. For the real time, I used DAC session.startForeground to obtain the data and then forced my data matrix to have the same number of points as the NR data number inputted. Similarly, for the simulation data DAT file, I loaded the DAT file in based on its name and made the matrix length the same as the NR data number selected. This function returns the data that needs to be analyzed into the global variable, in all caps, data, and is used in the next two helper functions. The display signal receives the data from the previous helper function and uses that data to find the amplitude, the DC, the AC RMS, the power, and it finally plots the signal. So to find the amplitude, I found the sum of the min and max voltage and divided it by 2. As for the DC value, I took away the offset by subtracting the average of the data with the dataset, and then subtracting the max of the original and offset data to get my DC value. As for my AC RMS, in my report I explained that originally, this function was going to be 4 if statements regarding the different modes because each type of the signal had a different way to find the AC RMS. But thankfully, MATLAB has a function called RMS that takes in the data points and finds the AC RMS value. Finally, for the power, it's simply just the square root of the AC and DC values squared and summed, and at the end I plot the function with respect to time. The final helper function that I made was display f of t, which finds the fast Fourier transform plot, the peak voltage frequency, and the period. It also spits out the acquisition time and the sampling per second. I used the MATLAB f of t function and the documentation on it to figure this out. One thing that was important was removing the offset from the data by subtracting the data and the average of all the points. I then found the f of t using the unbiased data points and divided it by the NR data, and used only half of it because it mirrors itself. To find the maximum frequency, I looked through the f of t data for the maximum voltage and set it as a matrix of 2, max f, index. I then extracted the index where the max voltage was, and that was the frequency. The period is found by the reciprocal of the frequency, and at the end I plotted the frequency to the f of t values. Now I will show you a demonstration of my actual app. Okay, so this is my app. As you can see on the user interface, there are two axes, the time domain signal plot and the f of t plot. Underneath the plot are the values needed to obtain when we run the app, which is like the min and max voltage, the amplitude voltage, the DC and AC RMS voltage, and the power in watts. On the right, we have frequency, period, acquisition time, and samples per seconds. To supplement this, we also have an AC, RMS, and DC voltage gauge, just for visual appeal, I guess. We also have the status bar at the bottom. And as for user input, we have the NR data points and it can be changed from 1024 to, it can go up by intervals of 1024. There's also the mode where we can select real time, sim sine wave, sim square wave, and sim triangular wave. And finally, to my right is my cat's knob value changed callback function that I mentioned in the presentation. If you change these, you can get different pictures of my 3 cats I have at home. This is Mini Cat. This is Major Chonk. He's a little bigger than Mini Cat. And then I also have Cloud Cat, a very stubborn cat. I will now demonstrate my app. We'll start off with 1024 data points on real-time mode, and if I just click on this, so it changes to working, it turns green, and the status is acquiring data, and this is what I get. And yeah, it's pretty nice. We have 3 peak points here, or peaks I guess. It seems like based on the signal, it looks like my computer has a square wave. We'll keep moving on. We'll do 2048 in real time. This will take quite a bit of time, I guess. It'll probably take like, what, 15 seconds maybe? Meanwhile, you can just look at my cat, I guess. Oh, 17 seconds. Okay, yep, same 3 peaks. And this signal. We also have all of our values down here. Let's move on to our sim sine wave. Let's just go back to or let's just do something. 4096. We'll acquire data. It should be pretty fast. Yep. So our sine wave, as you can see, has 1 peak. You can't really tell, but this is a sine wave. Oh wait, maybe you can? No, you can't. Whatever. Let's just go back to the 1024. Oh, this looks a little better. You still can't tell, it's okay. At 1 peak still. Moving on to our sim square wave, we'll do 1024 again. Square wave. So we have 3 slightly distinguishable peaks. This looks like a square wave to me on this signal, on the time signal. Looks pretty similar to my real time, so that is what I'm basing it off of. If we go to 4096, we can acquire data, and this is a blob of, I guess, square wave. And we have 2-3 peaks still at around 10 frequency, or 10 hertz, not frequency. Finally, let's move on to the sim triangular wave. So we have 1024 again, we'll acquire, and the triangular wave has 2 dominant peaks, I guess. This looks more like a triangle wave to me. We can see one frequency at 9.727 hertz. If we move up, let's just go, how far can we go? Okay. We have one dominant peak right here, and this is the triangular wave signal. The frequency, the hertz at peak is 9.877, which is shown here. And I think that's about it for my project. Thanks for tuning in. Here's another picture. Yep, that's about it. Thank you.